Hey everyone, welcome back. So before we start the video, I want to give a huge thanks to every one of you who supported the channel over the last couple of months. I didn't thought, to be honest, that the channel would hit the 1K. And I didn't thought even that this huge amount of people are going to be watching this series of videos or the reverse engineering series of videos or the micro corruption series of videos. But it's actually really interesting and I'm really happy that my videos are helping people learn something new. So thanks again to every one of you. And if you feel like that the videos are helping you, you can just share them with your friends, with the people that you think that might help them too. Yes. So what are we going to be doing today? So today we'll be adding up another video to the reverse engineering series. So we will be working on an interesting subject, which is anti-debugger. So we'll be using the anti-debugger to try to play around some stuff like that, like around the binaries and that, just to debug using the anti-debugger. So I think a lot of people just love the video of the GDB debugger, so I thought it's time just to show them another way to debug binaries, but this time using IDA. So for the people who don't know what IDA is, IDA is a, let's say, the compiler, a debugger, a tool that we actually use a lot, for example, in reverse engineering. For example, if you go and type in IDA Pro, you came across this little tool that is really interesting and that is really helpful. But I'm not the kind of tool person that would say that without IDA we can't do anything. Well, the interesting thing is IDA is a tool and it can help you, but IDA is not everything in reverse engineering, and you can even stay updated with what is happening in the reverse engineering without using IDA. Well, there's a lot of other tools such as IDA, for example, Ghidra, Binary Ninja, or whatever. At the end, they are all tools, but what matters is that you understand exactly what is happening before diving into tools. So that's why I have started the series with explaining different topics in the computer science, and then coming to use, for example, such a tools, well, naive tools such as GDB, and then to came back to use tools such as IDA. So using that way, we can have a foundation about what is happening. So we will be practicing today on the Flare-On CTF. So for the people who don't know what the Flare-On CTF is, the Flare-On CTF is a CTF that is dedicated to reverse engineers, and basically all the challenges are going to be binaries or stuff that is related to reverse engineering, whether a game, a binary, an APK, an Android application, I don't know, an iOS application or whatever. So basically it's going to be dedicated to reverse engineers. So today we will be practicing on the challenge 6 on the Flare-On 2014, which is the first edition of that CDF. And one other, let's say, interesting fact is that this edition of this year is going to be in 6 days. So if you are interested, you have to play that. You have to play in this edition. Yes. So the first thing that you have to do is you have to download the challenges, and the password, well, the password is not actually Flare, it's actually malware, but I'm gonna be just to gain some time, to give you some time, I have just linked the binary that we will be working on today, just in a link in the description. Yes. So if we try now to check out what we have, so by pressing ls, we see that we just unzipped what is in the challenge text. So we have a binary. So this binary is actually an old 8664 version, static linked, which means all the libraries are inside of the binary, and it is stripped, which means that we don't have any access to the symbols. Okay, so one thing that I have to say before you do anything, you have to just set up a virtual machine, or let's say a machine that you have, for example, I don't know. For example, you might have a machine that is in your home that you don't need, for example, or you don't, for example, care if that machine got infected or something like that, because this binary is a malware. So you have to run it in a safe environment. So yes. So when we run, for example, the binary, we have that the result is going to be no. So that means that the binary is not giving anything. But if we have to try, for example, to give it argument, for example, AA, it's giving none now. Okay. But if we have to give it, for example, something really long, it's still giving none. But if we have, for example, gave another argument, it's giving now bad. And if we give another argument, it's going to be giving another output. And if we keep giving, it's going to be giving the same output. Now the interesting thing, so that means that um, the minimum amount of arguments needs to be passed is 1, and the maximum is 3. After that, he's not going to be accepting anything. So, okay, so if we try to check just by doing some dynamic analysis as we have seen, just by running the program, just to understand the behavior of what the binary is doing, I think it is time just to throw that binary inside of IDA. So I'm going to be just using the IDA Pro 64 version, since the binary is 64-bit. And I'm gonna be loading that binary inside of IDA. So it's gonna be taking some time to load the binary into IDA and to just check out what is happening inside of it. And one thing that we can mention or that we can notice is that there is a lot of functions. So that means, so it's a kind of malware behavior that we've seen a lot in, if you have done, for example, malware analysis or stuff like that. Even though in the malwares, there is a lot of functions. Okay, and another thing is that because it's statically linked, so basically you might you might just stumble across a lot of functions. Okay, so just now by trying to find an entry point into something like that, for example, by clicking on the sub, we see there is a lot of stuff that is going to be happening. And to be honest, I'm more of a static reverse engineering guy, but when it comes to a lot of functions and stuff like that, it will be hurting me a lot to just try to understand everything that is in the binary. And a smart move can be just to try to figure out a way on how you can approach that. Well, the best way to approach stuff like that, for me at least, was to try, for example, to find the strings that was just outputted by the binary inside of the code to just to find an entry point that I can analyze from. Okay, to check out, for example, the strings inside of the binary, you can go to View, open subviews, and then go to Strings. And then by searching into na, you came across a lot of actually nas, and you have to find exactly where that na is. For example, if we try to check, for example, bad, well, bad is actually not listed in here, but for example, it can be that bad message. Who knows? Okay, so this is the read-only data section. Okay, now it comes to me another interesting approach. Since we know that all the strings that are inside of the programs are either in the read-only data section or in the data section, or it can be, for example, in the BSS section. So I thought if we can just figure out a way on how we can just check the read-only data section and just try to check, if, for example, if the bad message is there or not, then we should be able to know or find an just a cross reference to that string. So how do we do that? So to do that, we can just simply, for the first thing to do is we need to find the offset of the beginning of the read-only data section. So how can we find that offset? So we can just simply use the tool readelf or the command readelf just to get informations about that binary. And as we can see, this is just general information about the binary, and then we can just have a look at the section headers. So you want to have the read-only data, which is this one. So the beginning of the read-only data is actually at this address. Now, another interesting question that came to me when I was trying to solve this challenge is, how do I know, for example, if this address is not randomized? Well, the mitigation that is going to be randomizing such addresses is the pi. So we to check out if the pi is there on the binary or not, I just run a simple bound check sec to check if the mitigation, what are the different mitigation that was on the binary, and it comes out that the pi was not activated, which means that there's no pi. So that means, for example, if I take this address that I was taking, which is this one, so that means that the same address is going to be given if I tried, for example, to go into the IDA and check, for example, if I can go to it, for example. just by doing that, we came across the read-only data section, which is the beginning of the read-only data section, which is a kinda interesting. Yes, and then and another thing that the Y is going to be doing, for example, it's the same as the SLR. I don't know if you have watched the micro corruption series or not, but I highly recommend that you watch the micro corruption series to understand more about the mitigations such as SLR, buffer overflows, and stuff like that. So it's completely for newbies and intermediate levels, so you should check that out too. Yes, so if we go back a little now, if we try to analyze what this read-only data section is having, we see a lot of interesting things. For example, more SSH switch install. So it's a kind of malware behavior that we see a lot in malwares. So this malware is basically trying to see antivirus. So this might be, for example, the antivirus. He's checking, for example, the different antiviruses that are in the computer that is going to be executed and stuff like that. But if we came back a little down, we came across the message bat, which is the one that was in here, for example, when we run using two arguments, which is this one. So this is the kind of entry point that I was searching for. So by clicking on the A bat and by pressing X on the keyboard, you came across the cross reference. So by clicking now on the cross reference, we see all the cross references to this bad string. And if we click OK, we came across the logic that was calling the bad. Now if we try now to click F5 to get a decompiled version, which is the powerful utility of IDA is basically by having a decompiler now, we can have a decompiler in front of us, which is really interesting. Now, by doing that, so we came across this block. So the bad was called in this if block. Now there is a lot of garbage code that was actually loaded before the if, and that is really hurting to be debugged if you are going to be statically reverse engineering all of that. And by reading that code, we actually came across a pattern that I've seen a lot in many codes, and especially C codes actually, which is this one. If the A1 is superior to 1, then you have to check the str length or the string length of the A2 plus 8, and if it is different to 10, then you are going to be printing bad, which means that the length of the A2 plus 8, so A2 should be pointing to a string actually, which is, as you can see, a constant character with a double star, which means that it's a pointer on a string. And with the A2 plus 8, he's actually accessing some kind of case. Well, to be just generally explaining this, so the A2 is basically pointing to this too. For example, when you have executed the binary, so this is the argument. So the A2 plus 8 is pointing to the first argument because A2 is pointing actually to the name of the program, and by doing A2 plus 8, you are pointing back to the first argument. And it is actually plus 8 because we are working on a 64-bit and the addresses are all on 8 bytes. So that's why we are actually adding 8. Anyway, so if it is different to 10, then we will be printing the message pad. Otherwise, we will be going into this block of code that will be just calling the v3 and calling it with this function that we don't know exactly what it's going to be doing. And then he's going to be iterating through the length of that argument and then XORing each character of the v3 with the 0x56. Now for example, if I'm gonna be just trying to statically engineer this code, I'm gonna be just setting the assumption that the v3 is not going to be having, for example, the same values as the second argument, which is this one. For example, it's not going to be AA. Then this is gonna be hard because I'm gonna be, for example, now we have to make sure that we will be setting a breakpoint. So just to set a breakpoint in IDA Pro, you can just simply go in here and set a breakpoint. And then I will be just trying to show you how to set up the debugger and all of that. But we have to set a breakpoint in here and check if the v3 is going to be having the same values, or we can just check it in here. So we have two ways. We have to either set a breakpoint into this line or into this line. But we can just simply set a breakpoint into this line, so it's okay. So The other assumption is that the v3 is going to be having the same values as the second or as the first argument, which is AA. So he is going to be comparing what's in the what's well, he's going to be XORing what's in the second argument with this byte, which is 56, 0x56, and then he's going to be comparing. So this is actually a comparison because, well, there's no actually str compare or something, but this is from the pattern of the number of the parameters and the parameters that were passed to the function. We just can conclude just by looking at this function that this is going to be doing a compare, because it's taking the v3, which is the result of the loop, and then another string which looks like something that is encrypted, and then 10, which is the size of the argument and is actually the same size as this one. And if it is not 0, then going he's going to be giving bad, which makes sense actually. Okay, now just by looking at this, we have to find a way on how we can debug that. So to debug that, we have to set a breakpoint, as you can see in here, and then we have to set up the debugger. So to set up the debugger, you have to go back to the debug server. So as you can see, I'm already on the debug server and I'm launching that. So I'm gonna be just closing the debug server. So I'm basically, you have to go to program files, your folder of the IDA Pro that you have, and then you go to the debug server, and then you will find all the debug servers that you have. For example, in this case, I have the Android server, I have the ARM Linux server, a Mac server, Windows server, whatever. So in this case, we are going to be debugging a Linux 64-bit ELF binary. So I'm going to be using the Linux server, but with the 64-bit version. So once I have launched this server, I need to find a way on how to connect to that server. So to find a way on how to connect to the server, you need to set up the debugger. So I'm going to be setting a remote Linux debugger, and I'm going to be clicking basically on the run function. I'm going to be running something. So the parameters are going to be the parameters that we will be passing to the program, such as this ones. And for the host name, I'm going to be setting localhost since I'm running the debug server actually on my local machine. So I'm gonna be setting localhost, and the parameters I'm gonna be some 1, 2, 3, and I don't buy it, for example, just as an example. So I'm gonna be setting before that another breakpoint into this f, since I'm gonna be trying to check if the length is, if the a2 plus 8 is actually the first argument or not, as the assumption that we have set, and the a1 is actually the argument counter, since he is just checking if it is superior to 1 or not. So by now going back a little, so yes, so the parameters are going to be 1, 2, 3, and item byte, for example, and the host name is actually localhost. And yes, by doing that, so let's try to see. Okay, and before just doing that, I have just missed the point, which is the point is that before doing anything, we have to make sure that in the debug server, as you can see, we have also the binary. So the binary should be inside of the debug server folder too, which is something really important that we have to do, because actually if the debug server didn't find the binary in the same path, he will be trying to actually copy that binary to his path, but since the debug server is actually in the program files, it does not have the permission. So IDA is not having also the permission. So you have to copy that manually to the debug server. Maybe there is another way to do that, but this is the way I've been doing that. So yes. So now if we try again to run the program, what do we have? So keep copy new. Okay. Okay. So as you can see, the debugger is somehow not working, and the debugger thread has exited, as you can see. So there is a problem in that one. So there is a kind of problem that we have to debug. If we try to reopen the binary again, yes. So if we try to reopen the binary again, I'm pretty sure, okay, that is working. So yeah, okay. If we try to set up the Linux debugger again, so I'm gonna be setting localhost and 123 and item bytes, for example. Okay, before doing that, we have to make sure about something. We have to make sure that the analysis has completed. We'll just wait a second before the analysis is completing, before IDA completes his analysis on the binary, because it's starting, he's going to be taking some time. Yes, I have finished it. Now, just going back a little, yes. Okay, copy new. Oh, we didn't set the breakpoints again. I don't know, somehow it's crashing whether I'm opening that on a new one or whatever. Okay, just a second again. 144. Okay. One more loading. Loading that again. Okay. So what are we going to be having? So it's loading. We wait a second. Few seconds actually. Okay. So just to make sure that read-only data address is actually, we have to note all those things. So read elf dash all of the binary. So I'm gonna be grabbing specifically on the dot read only data. So it is this one. I'm gonna be noting that one. So I'm gonna be jumping back to this address. Let's get back a little to the bad. Okay, so this is the bad. By pressing cross reference, we get back to this address. Gonna be decompiling that one. Okay. Okay, cool. I'm gonna be taking that address also of the bad address is at this one. Okay, I'm gonna be setting a breakpoint in here and another breakpoint in there, and the Linux remote debugger. Okay, yes, 103 item byte hostname localhost. I think there's a problem. Okay, copy new, copy new. Okay, the debugger has worked now, but the debugger has exited. So somehow, if I try to rerun that again, okay, but it has exited to another time. So that means that when we try to debug the binary is not going to be debugged. There is a problem and there is a sick fault that is happening, or there is something that is happening inside of that binaries that is not going to be letting us debug. So this is actually an anti-debugging technique that is happening, and we can just now at this point, if I can't debug that binary, then there's a problem. So I thought of something. I thought of a way of how I can try to figure out exactly how we can know that the binary is debugged or not, or if the binary is implementing an anti-debugging technique that we know. So the first thing that I tried is I tried to use the command ltrace to figure out what are the calls that the binary was doing when it was calling, for example, with 123 and item byte. I was just trying to figure out a way. So when I tried the ltrace, actually, since it is a script and there's no dynamic symbols and dynamic string and all of that, I couldn't use the ltrace. So I thought of a way of using just the strace. Now the question that comes in here, what is the difference between ltrace and strace? Well, ltrace is actually used for just tracing the libc functions calls, which means, for example, if there is a function to the printf, malloc, I don't know, scanf or stuff like that, ltrace will make sure that we can trace them and see the parameters that were passed to these functions, and just to check and see what is the behavior of the program. And strace is used to tracing the system calls that was called by the binary itself. So for example, let's suppose you are having a binary that is, for example, going to be doing a syscall to the exit. strace will make sure that if this call is called, then um, then we will be sure that the strace will be tracing that one. So strace is used for system calls and ltrace is used for libc functions, just to tracing. One is used for tracing this is called, one is used for tracing the libc functions, for example, such as printf, malloc, or whatever. So this is just a simple explanation. What is the difference between ltrace and strace? Now the question that comes into your mind is, how did I know that I'm going to be just debugging with two arguments? So I actually used strace to know that. Well, I tried to run the strace just using, for example, one argument, and as you can see, it's going to be simply calling the exec v, since that is the first call that is going to be done with the kernel. And we have the uname. Well, break, I don't know actually what those syscalls are going to be doing, and I have skipped them since I was focusing on more what's going to be happening, which is the write. But when I tried to run with two arguments, I see another interesting syscall, which is ptrace. Now, if you have watched the video of the anti-debugging techniques and the patching video, I'm pretty sure you are familiar with the ptrace. So ptrace is a simple implementation of how you can check if the debugger is present or not. So this is why IDA keeps on crashing and exiting, because simply there is a bit trace that is inside of the program or inside that malware that is going to be not letting us debug the malware and understand exactly what is going to be happening. So ptrace was implemented. So if we try to run that with three arguments now, it's not going to be giving the ptrace. So that means that the only possibility that is implemented, or the anti-debugging technique is implemented with two arguments. So that means that the intended way to solve the challenge was to use two arguments, and we have to figure out exactly what are those two arguments. So this is the core of the challenge, and it's actually not an easy one, to be honest. This challenge is not easy one. It's not easy at all. Well, for some people it was kind of easy since they knew how to deal with such malwares, but it wasn't that easy for me at least. Anyway, so by running with two arguments, we came across the ptrace. So the first thing that came into my mind now is, if we have, so I'm gonna be saving that to the database. Yes. Okay, since I have to load every time, since the IDA Pro is crashing each time it has a debugger that is present. So now we have two approaches to just go along the way. The first approach is go and find ptrace inside of this, all those functions, which is not easy at all. The other easy way is to simply add a dash e to the strace to give you the address of where the ptrace was called, which is this one. And since the addresses are not changing, we can just simply press G and go directly to the address, which is this one. And as you can see, this is where the Linux ptrace syscall is happening. If we try to cross-reference where this function was used, we came across that this function is going to be using ptrace, and then it's going to be returning something. Then there is two logics to be there is two logic that is going to be happening. The first logic is going to be given as a program receive signal sig uh, sig EGV, and the other one is this one, which is the logic that we want to go to. But there is this GZ, so we can simply reverse the logic of the conversion and make this ENZ, which means that jump if not equal, or jump if not 0, which means that the zero flag, if the zero flag is going to be set, then it's going to be going to this one, which is probably going to this one because the debugger is present. Otherwise, we jump to this one. And just by checking that, we actually saw that the program received SIGV in the program received signal and the segmentation fault is happening. So this is just simply why this is happening. We can patch that directly by going to edit, patch program, and assemble, well, assemble, or yes, assemble, and I'm gonna be just quickly changing that from GZ to GNZ. Yes. By doing that, we see that the GNZ now is happening. Now I need to export that changed or that patched binary, so apply patches. So this is the backup. So I'm gonna be creating a backup basically, and this is the new one. So press OK, and the applied patches is happening. So we have to load now the new binary. We have to load the new binary. So if we try to load the new binary, so this is the new binary. So, and another thing that we have also to do is to make sure that this binary is the same as the one in the debug server. So I'm gonna be replacing the other one. Okay, so the binary is still in the analysis port, so I'm gonna be jumping to the bad address directly. So this is the bad address. Press F5 to decompile the code. And I'm gonna be setting a breakpoint in here and another breakpoint in here. So now let's try to run the remote Linux debugger with the different parameters, just 1, 2, 3, item byte, and local host as a local machine. Now if we try to run that, okay, copy new, and okay, and okay, and somehow we hit now the breakpoint. As you can see, if we press F9, we are now debugging using the anti-debugger, and the mitigation was somehow defeated that he was simply implementing inside of the malware. So if we press F7, we hit the breakpoint that is in here. If we go into the IDA RIP, it's basically in this one. So just one thing to mention here, guys, is that this will be containing the general registers. This is the stack view, this is the hex view, and this is actually the output if there is something that we want to interact, for example, with the IDA. If we want to, for example, script, for example, with the IDA Python or stuff like that, we can use this one. But anyway, this is the most parts that we will be using a lot, which is the registers. This is also the flags, the zero flag, the overflow flag, the TF, SF, sign flag, etc. So if we go back to the pseudocode and now check, for example, if, well, I'm gonna be stepping to that one, and as you can see, since the size is different, the A2 plus 8 is different from 10, then he's going to be calling the bad. Now I'm gonna be uh, just stopping the debugging, get back to the process options, and I'm gonna be changing that, for example, to 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, which means that we have now 9 characters. If I'm gonna be running using that parameter, so don't display that message again, please. And if we go now to try press F7, nice, we get back to another part. If we press F5, actually, we get into this one. So I'm gonna be skipping that function by pressing F8. And by pressing F8, I basically just jumped upon that one, and we have bypassed that block. So that means that the length is actually 10, and that means that this um, this parameter is actually the one that he is going to be checking. So that means that we are right. Now we don't have to complete all the analysis because we statically just came to the conclusion that he's going to be ignoring that the input with 0x56 and the result he will be comparing is this one. So if we try to decrypt this data, just XOR this data with this value, then we should be able to find exactly what is the input that he wants in order to bypass that. So to do that, we can just simply write a simple solver to that, which is not easy, well, not hard at all actually. Which is the key is actually 0x56, and the encrypted data is actually this one, which is B and G or whatever. So I'm gonna be just declaring an answer for element in the encrypted data. I'm gonna be doing answer dot append the element XORed with the 0x56, and then I'm just gonna be printing the result of that. So yes, so we save that, we run this solver for Python 3 solver Python. So this is the input that we should be having. So if I try, for example, to send that input, we get back to the process option. We send, for example, this one with item wide. We try using that input. What do we get? So I'm gonna be just skipping that one. So in order to get from a breakpoint into another breakpoint, you don't have to press F7. You can press F9. So now by pressing F9, we are into now this breakpoint exactly. So we are now in here. So the blue line shows exactly where we are. Now if I press F7, we are now just looping inside of that one. I wanted to set another breakpoint just to quickly go back into, well, we have breakpoint in here, so that's why he's coming back to that breakpoint. So we are now in the if. So I'm gonna be checking if the if is passed or not, and the if is supposed to be passed since we have get into another block. So that means that this is the first input. Now the interesting thing is that, for example, if I try to run it with that input, so this is the input, first argument, arg1. Argument 1 is that number. So if I try to run the binary with that argument and with the, well, I get program received signal sigv because I have patched the binary, and now he is assuming that since I have reversed the logic, when I try to run it without a debugger, he's going to be giving me the segmentation fault. So if I try, for example, to run that with the backup binary that we have, for example, this one, when we try to run it without the intended input, it's going to be giving bad. But when we try to give it with the actual intended input, it's going to be taking some time. So this is actually a sleep implementation. So the program is sleeping. So that means that the next behavior that we have to hand inside of the malware is this sleep function. So we need to find exactly where the program is sleeping, and we need to find a way to bypass that. So that means when we give the other, so that means when we give the first input, the program is going to, well, when we give the first input right, the program is going to be get into a flow of sleeping. So if you go back to IDA, well, the way to do that, you can actually keep on stepping inside of the malware to know exactly what is happening, or you can just, well, I simply try to find a way directly, but the way is actually by keeping on stepping just to gain some time. The address of the sleeping function is the actually 47 3D 6F, which is this one. So this is where the sleeping is happening, and you can find that out by figuring. You can just figure that out by keeping on stepping inside of the program until you hit the nano sleep. Well, if you go back a little, and we check out now the this part, so it's 47 3D 47 3D6F, which is this one. So we have seen that he's actually sleeping some kind of time, which is, this is the parameter that will be passed to the syscall, which is the sys nano sleep, and this is the other one. which is this one. So we have to find a way on how we can just get rid of that. So there are two approaches. The first approach is to change the AIX, the value that is in here with 0. That means that the program will sleep 0 times, or just completely get rid of all that. So how do we get rid of the of an instruction in assembly? We can just simply use NOP. So in case you don't know what NOP is, so NOP means no operation. So that means that the CPU is not going to be executing anything. So we can simply patch that directly. So I'm gonna be patching that with the change byte. So if we go and check what these bytes are doing, so we can simply use the online disassembler. So I'm gonna disassemble that and check what those things are doing. So the part that we will be changing is all that. So that means that the instruction that we want to batch are ending with 05. Okay, what is the opcode of the NOP, if you want to know? So we always choose the 64. So the NOP is 0x19, so that means I'm gonna be changing all those to 19s. 19s, 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 90, and another 90, and another 90. Okay, and I'm gonna be copying that. So if we try to patch that, we see there is a lot of knobs. We also have to patch those two. So since we know that it's ending with 0f, we can directly. So we have patched those two. So we have now to export the program. So apply patches to back. We have to create a backup. I'm gonna be naming that f since we already have a file that is named with this one. And yes, okay, so the applied patches are 14 on 14. Okay, cool. Now, I suppose we have to do the same thing. We have to take the new exported binary, and we have to throw it in the debug server as the first step. What else? So we also have to load the new binary that we will be working on. So I'm gonna be not saving that to the database, and I'm gonna be loading the new binary. So let him take some time to load the binary again, the new patched binary actually. Yes. Now the next thing that we will be doing is actually we have to keep on stepping on inside of the program, but it comes out that the next step that the program is going to be doing is just after skipping the sleeping part, is that he will be coming across the function that is 141180 141164. So what this 141164 is going to be decoding some shell code that is going to be inside of the there's going to be inside of the malware, and he's basically going to be calling that function. Well, this is what will be happening. So he will be loading some some variables inside so some parameters to this function, which is basically the size of the shell code and the shell code itself, which will be actually inside of the variable 440. So actually I don't have any um, any access to it for now, but we can set a breakpoint in here, and we can set a breakpoint in here just to check the parameters that will be passed. So remote Linux debugger, so yes, I'm gonna be passing the right parameter, right first parameter, and then item byte, and then host name is going to be localhost, and then okay, some time before he loads copy new. Okay, and we hit the breakpoint. Okay, cool. So if we want to know what this variable 440 is going to be having, and this one, what this one is, will be also going to be having. So to pass the parameters in the 64 convention, they are passed in the EDI, ECI, and then ECX, and etc. So we can just check that. For example, if you have forgot, you can just type in x64 calling convention. Check just the Microsoft, well, Linux. It's taking some time. Is there any kind of table? Yes. So the first one is ADI, RCI, and then RDX, and then RCX. So in this case, we have ADI, okay, ADI, this is ECI, this is RDX, and this is RCX. So those are the parameters that will be passed. And this is actually a pointer that points to the first parameter that we will be decoding. After doing that, if we try, for example, to just press F8 to step aside on that calling function, and the RIP now is pointing to this one, which is actually this instruction. So if we try now to step a little, if we keep on stepping, we see that he's going to be calling the RDX. And this is actually um, one of the pretty famous behaviors that you can see when you try to see some shellcode that was loaded on runtime. So that means that there is some kind of shellcode that was encoded and, for example, some kind of encryption, and then it was decoded inside of the process at runtime. Now, if we try to press F7, we see that we are now executing some code that is in the stack, and he is actually a shell code. That means that there is some executable code that is in the stack, and since there is no errorx as a mitigation, we can simply do that. So if we jump back a little, we see now pretty famous instructions such as rotation right, a rotation that is going to be happening to the array-x. So the array-x is containing now the second argument that we will be passing, which is iron byte. And each time he will be doing something to one of the characters. So in this case, for example, he's going to be taking the I, and he's going to be rotating it with F2, well, rotating it to the right with F2, with 0x F2, and then he will be comparing the result with 1B. So that means that the result should be 1B in order to be right. So we can reverse that basically by rotating left the 1B to the F2. So just to explain to you what is going to be happening. So for example, he's rotating the I. So I'm gonna be rotating. Let's suppose the flag is I don't know, Flare CTF, for example, Flare. So he's going to be taking the F, rotating it with 0x F2, and noting the result. For example, the result in this case is going to be 1b, which is 0x1b. So what he did actually is he needs to make sure that he wants to make sure that whatever you give something, it's taking 1b. How do we reverse this? So to know to get to the f actually, well, I don't know if it's actually needs to be if something needs to be an f in here in this case or not, but to find, let's suppose it's going to be unknown, which is x. To find the x, we need to do just simply a rotate left, which is the reverse order of 0x1b with 0x f2. We can simply find or know exactly what is going to be happening. So we can now just write a simple solver, because each time he will be adding one to array x, one to array x, one to array x on this shellcode until we get the flag. So to simply do that, I have stumble upon this interesting one, which is containing the implementation of the rotate left and the rotate right in Python, which will be just saving us some time. I'm gonna be using them in the solver that we will be just creating together. So vim solver Python, um, we can just use them directly. So I'm gonna be just just commenting that. Okay, we can just try to do them. So one thing that is really interesting in this is that all the characters are on 8 bits, since we have 256. So the maximum bits is going to be the maximum bits are going to be 8 in this case. I think we don't have to set them. We can just directly use the rotate left, and we can now test on the other version. So okay, so the argument 2 is going to be a list, and what do we have? So we have to find a way when we can initialize those. So for x, and for example, how much do we have? So we have to count those things. we have to count how much block do we have, because each block is going to be pointing to a character. So let's suppose I'm gonna just be using that on, for example, retrieve the first 10 characters of the flag, for example, in the range of 10. So x dot, for example, argument 2 dot insert, for example, x, and I'm gonna be inserting x and, for example, 80. Okay, so that's some, you can just initialize it with 0, for example, which is a better way. If I print the argument 2, it should be containing zeros, yeah. Okay, so I want now to I want now to check out the rotate right thing. So we want to know, for example, what is the character is going to be for this one, which is a rotate left 0x 1b with 0x f2, which is this one. So just before doing that, well, let's get the result, and then I'll be just doing another thing, which is 108. I want to know the character that is pointed to. I want to know the character is pointed to by this one, which is L. Okay, so I'm gonna be testing that with what is in the IDA, because if we try to step inside of the IDA, so the GZ is not taken, and he's actually taken as to a sys exit. So that means if the first character is wrong, he's not going to be checking the other ones. Once he finds the character that is wrong, he's not going to be completing the check process. So if I try now to set just the first character as the one that is going to be right, which is in this case L, and try to check if we are going to be hitting the right character or not, then we have completely just find a way on how we can reverse the code. Okay, then we want to step inside of it. Just a second. Please don't show this message. Gonna be just taken out of this breakpoint. We don't need it anymore, so click RDX. So now he's going to be taking the L, he's going to be rotating it to the right, and then comparing what's in the RX, which is actually 1B. Okay, cool. Yes, we have bypassed that one. So that this is the logic that we will be using. Okay, so we can complete that with the other blocks. Okay, we can just complete that with the other blocks. And now, okay, just to get ahead. Okay, just using that one. Okay, so vim solver.python. So we can just assign that, for example, to uh, we can just assign that, for example, to the argument that we will be using. So argument 2 of 0 is going to be the character that is in there. Well, I don't know, we can get rid of that, and we can make it this way. Argument 2 dot append, just to get some characters of the flag. Or is it a bad way to do it? I don't know. I think that's not the best way to do it. I'm gonna be repeating this here a lot, so for in range of 16, argument 2 is going to be having dot insert the 0x like element, and with the 0 like whatever, and argument 2 of 0 is going to be having chr of the rotate left, etc. We don't need that chr anymore. and I'm gonna be just taking that. So argument 2 of 1, argument 2 of 1 is going to be having. So what do we have? We are comparing 13 with the XORing. So how do we reverse the XOR? We simply XOR that with that one, and then we keep another. We do another XOR, and then we do another XOR. So we are going to be XORing four values together. Okay, 0x with that value, 0x b3, b3, and we are going to be XORing it with f2 and with 0x42. Argument 3 is going to be XORed also. Now what do we have? So we are comparing the 1f. So okay, so we are XORing 0x1f with 0x71. What about the argument? Well, this is the argument 2, 2, 2, 3. What is the next character? So 0x b0 is going to be rotated right, so we have to rotate it left. So rotate left b0 with how much? 0x bc, and then you add this one. So how do we reverse the add? We do a sub, so minus 0x a3. That's pretty simple, right? It's not hard to reverse that. Argument 4 is actually, what is the argument 4? So argument 4 is just comparing that one. So 0x e8 plus 0x 79. Since we are doing a sub, we can just simply do an add. Argument 2 of the 5 is going to be, so we are doing e sub, so it's going 0x f6 plus, since there's a sub, we do the reverse operation of the sub, which is the add 0x28, and then all this operation is going to be inside of e rotate left. Since there is e rotate right, we should be doing e rotate left of exactly 0x82. Okay, I suppose we are cool. Yes. Those are, I think this is 6 characters. I think 6 characters are okay. So now we can just simply try to get in the range of 6. Okay. I think we can just simply get directly, but we have an index that we have to check. So okay. So for index item in, we have to just simply enumerate enumerate exactly the argument 2. We can just print the index. We can just print directly the item, and with the and equals to that one. Let's try to see what it's going to be doing. There's a problem. There's a kind of problem, I think. Argument 2. Okay, there is a kind of problem, I think. Well, we are actually, the first thing is that we are not showing the CHR of the item, and one other thing is that we should make sure that the character is in the range of the characters that we know, which are 256 0xFF. I think that's cool. Okay, so this is the first part of the flag. You can just complete the flag just by completing all the blocks. I just wanted to show you how we can simply now use the anti-debugger to find a way on how you can debug, for example, your shellcode. You can actually do it using IDA-Pro. You can use it GDB. You can use Binary Ninja. You can use whatever you want. What matters is that you learn at least how those mitigations are happening. For example, we have tried to break down the ptrace again. We saw that there was some kind of sleeping that was happening, and then we somehow reverse engineered what is happening for the first argument, and for the second argument it was a simply shellcode debugging, I guess. Yes, I hope you have learned something new. Don't forget to hit the sub button, don't forget to follow me on Twitter, and if you have any kind of recommendations of challenges that you want to play, for example, at it, or that you want me to make a video on, you can just simply put it on the comments. And if you have any kind of questions, yes, feel free to write a comment or send me a message on Twitter or do whatever you want. Yes. Have a nice day. Bye.